Hi everyone, thank you for joining. In this presentation, Miguel and me going to tell you about Adyen's journey to build machine learning feature platform that fits Adyen's technological landscape, but more importantly fits Adyen's growth ambitions, and how feature platform domain-specific language helps our users wire multiple moving parts together. Let me start by briefly telling you about what Adyen is and why machine learning is a crucial part of our technological stack. So, Adyen is a payment service provider, which means we accept payments on behalf of merchants and process them. In other words, we make online payments happen. We deal with the money flow from shoppers to banks to merchant accounts. Since the early days of online payments and e-commerce, there was various types of fraud that banks and shops had to deal with. And in the world of online payments, entire ecosystem of companies and services exist with the sole purpose to tell legitimate payment, legitimate shopper from a fraudulent one. Machine learning is not new to Adyen. We've been running machine learning models in mission-critical flows since at least 2018. Here are some examples. Payment flow optimization is the model that finds best combination of payments that we send to Visa and MasterCard in order to increase chances of payment being accepted. Shopper fraud, a model that highlights the payments that have high chance in resulting of money-back requests. Bot detection model, the model that tells payments coming from legitimate shoppers from payments coming from bots and scripts used by fraudsters. By the way, the last one, scripted attack model, was presented yesterday by Yap and Itzel and was a great success. To give you some perspective, nowadays, Adyen feature platform handles 40,000 requests per second, over 300 terabytes of machine learning features data. Historically, at Adyen, creating a new feature for a model was rather cumbersome and anything but user-friendly. So, once the data scientists got an idea for a new exciting feature that would improve model performance, they would have to create a custom Spark code and put it in the Airflow deck. That step alone was already problematic and error-prone, since the code would run over a huge amount of data, and if it's suboptimal, it might run for days and eventually even crash, clogging the pipelines and trigger alerts downstream. Once a feature were produced, they would be stored in HDFS in the Delta Lake, which once again require manual configuration. Then, once the features are ready, data scientists had to prepare a metadata configuration file, which would tell the rest of the system how to ingest the features into Cassandra and how to make them available in the model inference flow. All these steps done manually by every data scientist team led to team's isolation, where each team would repeat the same steps and create same pipelines over again, often not sharing the findings and not sharing the code in between for some edge cases, such like handling null values, daylight saving times, point-in-time joins, window deduplication, and so on. Another problem became evident with introduction of Apache Flink, which happened relatively recently. The situation we found ourselves in was that in the inference flow, in the payment flow, the data was coming from Apache Kafka, features computed by Flink, stored in Cassandra, and used by payment service in the model inference. While in the training flow, the huge historical data stored in Hadoop, features computed by Spark, stored back in the Delta Lake and used for model training. But underlying features were still the same. So we needed to ensure that the logic used to calculate the features is consistent between two different pipelines. So back in the days, life of data scientists at Adyen was anything but peaceful. A lot of tools to manually configure, a lot of red pipelines, a lot of alerts, general house. If we wanted to make life of our data scientists easier and expand the reach of machine learning at Adyen, we need to improve the situation. So we decided to build a DSL. The goal behind DSL is that data scientists will not have to deal with tools directly anymore. They would define a DSL in the Python API. They would define the feature in the Python API. And from that definition, the rest of the pipeline would be automatically generated. So the code for Spark and Airflow deck generated not only production ready, obviously, but also taking into account all the learnings we found so far for the edge cases and so on. Feature metadata configuration no longer needed as it will be directly available from DSL definitions. Oh, sorry. Delta lake configurations also done automatically out of the box. The differences between various engines also handled transparently to data scientists. So to recap, why DSL was needed. A single API for data for machine learning features. One-stop shop for all data scientist needs. Single place to define a feature computation logic. Written in Python DSL, take care of differences between Spark and Flink or any other engine you want to introduce. Hide implementation detail from data scientists. Ideally, they don't have to care about pipelines in general. And facilitate experimentation, last but not least. Once features creation is not a cumbersome and painful process anymore, data scientists can actually focus on data science and not feature pipeline engineering. Now, as you have a little bit an overview about our struggles and motivations behind DSL, Miguel is eager to tell you about it in details.
Hello. Can you hear me well? Nice. OK, so how do we design a feature platform DSL that allows users to basically define their features in order to allow them to basically focus on model improvements rather than data engineering complexities, while at the same time not limiting them by taking away the flexibility on the features they can create? Allow me to start by showing you what this DSL looks like. And first, let's set some context. Let's pretend we're all the first machine learning science team at Adyen, trying to build the first fraud detection model for online payments. And we came up with an idea. We want to add a very basic feature to our feature platform, which represents the number of past frauds associated with the card for this given payment. For example, the count of frauds in the last 3 months for this payment. Since we all love the thrill of a live demo going wrong and some live coding, I'm about to show you with some Python, because this is a Python-based DSL, so it doesn't make sense to show it otherwise. First thing the data scientist has to do is define a class like this. Basically, hopefully you can all see well, basically something that defines your schema. In this case, we have a class, online payments, that extends from DSL data frame. It's something that's part of our framework. Then you specify the types of each field, and you have to say, by annotating it with this decorator, schema, where this data comes from. In an offline setting, because here in this demo we're going to be focusing more on features that are derived from Spark. On an offline setting, this comes from a Spark table source, which database is, doesn't matter, some database, and the name of the table is payments. We must also specify other metadata about this table, for example, how often it's updated. That's crucial for any type of ETL. So we have an online payments data frame, the data frame, but this comes from the payments table. We want to build a fraud detection system for online payments only, so we must filter out all the payments that happen in store. How do we apply a filter in here? By defining a method that basically is annotated with this decorated as well, the filter condition, and we specify, just like we would in Spark, for example, self.isInStore equals false. Now what we can do is we convert this to SQL and see what this gives. As you can see, this Spark SQL was generated that can be consumed by Spark. So we select the 4 fields from the database we specified, and we apply the filter. Simple. Now, we want to know which of these payments are fraudulent or not. And I know that there's another table that contains the fraud events, because frauds usually are only identified sometime after the payments happen. And there's this table, the frauds table, where there's another that basically identifies all the payments where frauds occurred. So we have an online payments data frame, a frauds data frame. What do we want to do? We want to join on the online payments information, the information about frauds, basically enriching the online payments. We want to perform a left join then. How do we do a left join with this DSL? We start by specifying a new class, online payments with fraud info, which extends the previous 2 classes. You'll understand why in a second. And then we specify the joining condition, So online payments.payment ID equals frauds.payment ID, a simple one in this case, and we specify the type of join we want to do. We want to do a left join. Now, we already have the join defined, but we have no field saying specifically, this is a fraudulent payment. How do we have a derived field like that? We can, since we did a left join, we can simply check if fraud date is null or not. And we can achieve that by specifying another field, now with the decorator that says it's a derived field, and that produces a Boolean. And we just say return self.fraudDate is not null, just like we would in Spark. Now, let's see what's the output of this in SQL. I didn't comment this one out, but now we have a bit of a more complex SQL statement. Allow me to walk you through it. First, we have a common table expression fetching the first query that you saw. Then another query for loading the frauds table. And then finally, we have the join definition from online payment schema model, left join frauds on the payment ID match. And we even have the derived field that we defined, fraud date is not null. So as we can see, we just defined a way for the user to manipulate the data in a way that's agnostic to the underlying engine, like Spark. And then they convert it to Spark. We also, because this class-based API can be rather limiting sometimes, we also start supporting recently a more data frame-like API, which allows for a more familiar interface and to provide more flexibility. So just like in Spark, the user can do df.groupby. I don't know what's happening, but let me close this one. df.groupby, aggregate count, and we're just counting the shopper cart hash. If we print this out, we get the exact same query we saw before, but with this aggregation in the end. Group by shopper cart hash and a simple count. OK, so we defined the data manipulation language in Python here. Now, we don't want users to simply start using these languages just because. We want to provide a bunch of tooling to generate features. That's the main goal. And that's where this DSL feature view class comes from. Instead of DSL data frame here, if you look closely, we have DSL feature view. And then there's a feature defined, payments in last 3 months. So over the last 90 days, we want to perform account aggregation over cart. But we haven't specified that it's over cart yet. So we must have that type of metadata here. We want to say the source for these features is online payments with fraud info. And the entities over which these features are being computed are shopper cart. Then we also, in any streaming type of system, we have to specify a timestamp for computing these metrics. And in this case, it's event timestamp. And update frequency again, because it's necessary for any ETL. And we can convert this to the most simple version of the SQL for these features. Hopefully run successfully, OK. And it's kind of similar to what you saw before. Oh, I forgot to. So if you remember, the feature we were trying to create initially was frauds in last 3 months. This one is very simple, right? This is just payments in last 3 months. How do we compute the frauds in last 3 months? Very similar to this one. We can just copy it. We already have a field that specifies whether the payment is fraudulent, right? So what we're going to do is change this from a count to a sum aggregation, and only sum whenever the payment is fraudulent. So when payment is fraudulent, then we sum. We convert the value to a literal, to a long, and we apply this aggregation. Let's see how this goes. And there it is. So group by shopper cart hash, sum case, when is fraudulent, then 1. And we have here the feature fraud is in last 3 months. But this is a very, very vanilla version of the feature. And as we mentioned, there's a lot of optimizations we want to apply before we get a feature in production. And that's actually what happens under the hood when we productionize these features. We apply all these optimizations on top of the logic before we convert it to SQL. And if I apply them here and convert to SQL, I basically get a SQL statement that's too large for me to explain here, with all the optimizations already applied. And that's what actually then goes to production. So now you get a grasp of what this DSL looks like when you're a data scientist using it. Allow me to walk you through some behind the scenes and how it works. For every operation between columns or applied on a single column, for example, this equality between two booleans, what's happening is it's returning a Pydantic object that describes this operation. In this case, it's a binary Boolean operator, as you call it, that describes an equality between the Boolean column is in store and the Boolean column that's always false. Then this is wrapped into a Boolean column. Any operation between two columns returns another column. And this is like a strongly typed system. So we built a strongly typed DSL that's Python-based. Kind of went full circle there. And this allows us to basically build validations, since this is all Pydantic under the hood, and also with MyPy, it allows users to early detect any mistakes they could have made that are at least detectable via type checking. What happens when a user defines a class, like the online payments that you saw before, is that this schema decorator creates another Pydantic object describing everything that's needed in order to load this data frame. So it says the columns, the filter condition, and the table to read it from. Then this schema decorator also attaches this model as an attribute of the online payments class so that it's later accessible for more downstream transformations. As you see here, a little on a similar note, but a bit more complex, how does the join work? The join schema decorator is creating another Pydantic object, the join model, describing that there is derived from two parents, the schema models that we defined in the two upstream classes. And yeah, online payments return the schema model. That's why you see the schema model here, and then the frauds on the right. It also contains all the other information. For example, how to derive the is fraudulent class, is not null, as we derived before. How to do the join, it's a left join. And from then on, we get everything we need to do the manipulations, all the information necessary. So hopefully, I'm being able to convey what's going on here. We designed the Python-based data manipulation language that's constructing like a logical tree using Pydantic objects of the data manipulations we want to apply to our data source. In this case, we defined two schema models that are joined together, and then an aggregation happens to produce the features. What we have then is another separate layer that can convert this to any type of basically, it converts the logical plan to a physical plan, right? It converts a bunch of Pydantic objects describing transformations to something that's executable by Spark or Flink. Since Spark and Flink have one thing in common, SQL, in order to minimize our amount of work, we are reusing SQL, since most of it is common between the dialects of the two. This applies to these two, because these are our main use cases so far. However, it could be easily extended to transform into any other type of engine, like Polars or NumPy. OK, so again, we define the data manipulation language, but we don't want just data scientists to start using yet another language. We want to provide them tooling for features. And so what was this that you saw, perhaps a bit small, the feature view decorated class that we defined in the end? Basically, this is a third library that uses the definitions created by the user and extends on top of this data manipulation language in order to automate the whole process. So just from these definitions, we can automatically derive the Spark logic, already fully optimized, that's necessary to generate the features, the Flink logic as well, all the configurations necessary to create the delta tables. We also generate the Airflow DAG that's productionizing these features, and, for example, the Cassandra table as well. As soon as, in order for a user to get these features live, all they have to do is basically write these definitions into our feature catalog. This way, upon the next release, they basically are enabled automatically in Airflow, and the DAG starts backfilling the data for those features. OK, now you get the gist. Allow me to walk you through some of the challenges we faced along the way. So first of all, as Vitalii described, I fetched this slide from him, there's a problem regarding where the machine learning scientist lives compared to the Flink, the engine. Because Flink is in the critical flow of our payments, and the machine learning scientist cannot simply start jobs over there. So how do we create a bridge? That's one of the main goals of the DSL. So when the data scientist is defining a feature that's supposed to be executed by Flink, they must specify, instead of an offline source, an online source. Usually, or so far only, it's a topic, a Kafka topic, where Flink should be fetching this data from. From this definition of feature, we can then derive a JSON file that describes everything that's necessary for the event for the service where Flink is running to basically productionize these features. The topic, but also the SQL that's supposed for Flink to run in order with the business logic to compute the features. Another interesting challenge, or maybe optimization that we included, was to avoid redundant data processing. Allow me to walk you through a very simple scenario. Think of a feature that's computed every day, but it's computed over the last 3 days. So a 3-day window updated every day. If you look very closely at day 5 over there, as the window moves, day 5 is being processed over and over. We're talking about the 3-day window, but we could be talking about the 300-day window, or larger. And we see 3 payments here, but could be millions. So being processing these events over and over is quite inefficient and something we wanted to optimize away. How did we achieve that? We basically introduced, we separated the process into a 2-phase aggregation. First, we basically performed a first aggregation on a partial window level, so in this case, on a daily level, by storing the partial feature values in an intermediary table. So for day 5, since these are counts, the partial values are simple. For day 5, we store the value 3, for day 6, the value 2, for day 7, value 4, so on. And then, in order to compute the final feature value for any given date, all we have to do is, instead of aggregating over the raw event level data, we just need to aggregate over the partial features table. So day 3, day 6 is just the sum of the 2 values in the partials table, which is much, much smaller than the raw event table. And so on. Day 7 is the sum of these 3 in this scenario. Another thing one of our main priorities while building this project was to speed up the development cycle for data scientists. So anybody who works with Airflow on a daily basis perhaps recognizes this image. It's the image, it's what it looks like when an Airflow DAG is catching up. So what's happening here is that every day, for every single day in the past, because for context, machine learning scientists, when they create a new feature, they need to backfill it to historically train their model with the right features at the right point in time, right? And they need to backfill the data, and they do it via Airflow by triggering a job, a different Spark job for every single day that's computing the values for that given day. What happens is basically this. So we have 3 different Spark jobs running with a lot of overlap between them. And so they are reprocessing the same data over and over there with a lot of overlap between them. And we are basically using the parallelism at Airflow level rather than Spark level. So we wanted to change this, but in order to change this, we have to change the way that the Spark logic also works. The way we found in order to fix this or to improve this was basically by changing the job to first compute the partial aggregation. So in this case, it computes the partial aggregations of the features for each day. And then it basically explodes those partial aggregations into all possible combinations of windows that are produced out of it, and stores aggregates all those exploded windows into a final feature table. This basically allows us to, in a single Spark job, to create to backfill the features with accurate values for each point in time, and in a much more faster way produce the accurate values. So this is what our setup looks like in the end for Spark features. Currently, I'm only focusing on Spark features. Is that we have a single DAC that runs on an hourly basis. Doesn't matter if the feature is supposed to be hourly, daily, or weekly. If it's not meant to be triggered at that moment in time, then the task is simply skipped. And however, if a new feature is introduced by the most recent change, or if a data scientist changed the feature, the DAG detects that and automatically triggers one of these jobs that backfills the feature for the entire period where the data scientist configured it to be relevant. So I guess that's it. There's no more time for optimizations. There were a few changes, a few others we had to do. But now we are more in an adoption phase. We currently have 3 teams starting to use these batch features, which by batch features, I mean features generated by Spark. And 1 team, since Flink is quite new at Adyen, we're starting slow, adopting the streaming features generated by Flink. I think some insights and some things that we wish we knew at the end that perhaps you could take away for your projects is that, for example, users don't love new languages. And even though that class-based API looked sophisticated and nice, it creates friction because it's something new. People are not familiar with it. So that's also why we started introducing the data frame-like API that I showed you for a bit, to hopefully make it more familiar, something already people know, PySpark. Also, most optimizations don't fit all features. So don't just assume your optimization you're implementing, it looks very cool, but because it's not going to work for every single case, so always make it configurable, always make it under a toggle, something we haven't always done and should have. And we're starting with Flink. Ideally, we want our system to be as simple as possible. So we have a lot of Spark expertise. That's why we invested so much in continue building these features with Spark to make sure we went the right way. But Flink is promising, and it's introducing new features daily. So perhaps eventually we could simplify our setup to migrate to Flink, but we can't tell yet. This is the current feature platform team. Laura, Jonathan, Vitalii, this guy, Antonio, Mateo, and Rodrigo. I left the team, that's why I'm not there, and these 2 are the ones that are taking over the project, heroes, and that's it. Thank you so much. Time for questions.
Well done.
And
Thanks very much for the interesting talk. This looks and sounds a lot like this declarative language in which you can specify features and data manipulations, like what feature stores like HopsWorks are able to do. I was wondering if you have looked into these kind of services, and if you did, if there was a reason that you didn't choose to use them.
did we consider HopsWorks?
I think the main reason we didn't went with existing frameworks is that we felt that it would be probably the same amount of work to fit those frameworks into existing Adyen ecosystem as if we would build something that really fits our needs. And
Yeah. I think one of the main candidates, at least for open source tooling for this, would be Apache Beam that we considered in the beginning. Perhaps HopsWorks, I don't know, maybe it's more cloud-based. I did not look much into that project. But for example, Apache Beam is an open source project, which we tried in the beginning. However, we felt it was more limiting than enabling, especially the Python API. So that's why we skipped Apache Beam at least and decided to build some custom things on our own.
Makes sense, we made the same choice.
should we even tell the sad story of a fist?
We used Fist for a while, but...
Yeah, we recently completed the entire cleanup to be sure. TLDR, we tried it. It didn't work for us.
It's no longer maintained.
Thank you very much, Vitalii and Miguel. I have a question. You increased speed of creating new features. It means that it's much easier to create features with the same logic. Do you prevent somehow data scientists from creating same thing several times?
Sorry, the volume was a bit too low. I couldn't hear the question quite well.
I'll try one more time.
Okay, sorry.
How do you prevent data scientists from creating the same feature with the same logic several times?
So how do we prevent? Oh, okay. There's no guaranteed way to do that. The way we try to improve that. So your question is, how do we prevent two different data scientists in different teams to create a redundant feature?
Yes, because with your tool, it's much easier because we can create more features.
Well, yeah, okay. So we didn't invest a lot into making sure that doesn't happen. The adoption of the tool is still growing, but hopefully, so before each team had to deploy their features in their own separate apps, completely separate. And now, as I showed, there's a catalog where teams have to put their features and we productionize from there on. Hopefully, since features will all be in a single catalog, people will look into it first before creating a new feature. But if we ever see a problem of features being redundantly created, we perhaps could find ways to identify that, but not yet. That's a great question.
Thank you. A quick question for clarification. So joining the streaming side with the batch side, you see you can configure it flexible, but are you assuming that within Adyen your data models in both settings are exactly the same and that the same transformations for all of the cases or for most of the cases would be equally applicable in both scenarios, or is that more or less going to be two separate definitions for most of the cases?
Okay, there's two layers to that. First is differences in logic between Spark and Flink. I don't know, a function behaving differently, and differences in sources, right? The data sources potentially being different. When it comes to the logic component of their going wrong, we try to avoid that mainly through testing, basically having agnostic tests that ensure that the logic in Flink is outputting the same as in Spark, which works, can always go wrong. It's the best we can do. When it comes to data sources, ideally the data source that's being used in an offline setting should be the same one, that should be a dump of the one that exists in an online setting and should be exactly the same. But we don't have validation mechanisms to ensure that yet.
Okay, thank you.
Hi, thanks for the talk. Full disclosure, I work at Hopsworks. I just have a question about, you mentioned point-in-time correct creating trained data, but I just saw an equality join there. But when you have different data sources producing data with different timestamps, so you have time series data, we often have to align the timestamps. So you had an equality join, and typically we do that. Again, full disclosure, I wrote a book on this, if you want to look at it. But I typically use it, and I had a paper at SIGMOD last year. It was basically saying it's an as-of join. That's how we do it. That's what a point-in-time correct data is. There's no as-of join support in Spark. So how are you implementing it in your DSL?
We implemented a custom one with Spark, basically. That's one of the biggest challenges we go through, making that join making it efficient enough to join on the massive amount of features. I think it's one of the biggest struggles we went on the last year, but we have to implement. We have multiple implementations of different joins for different types of features, basically. Do you support the?
Of course. I mean, but the other one, the last question, sorry, is real. We have a concept of real-time features, so features created at prediction request time.
Yeah.
Have you considered that, or is everything coming through Flink? What's happening in your case? So for clarification, a real-time feature is one that requires a request time parameter to be computed. So you perform the transformation on a parameter that arrives at request time.
That's something that we plan to look into next year. Right now, our Fastest aggregation is 1 minute. Yeah, 1 minute update frequency or 5 minutes of data, but it's still windowed features. And the real-time capabilities of Flink was the reason we opted for that engine. But so far, we haven't implemented those features yet. But it's on the radar.
I'll throw a last one. Do you know about incremental view maintenance? So incremental computation for feature computation. So Flink,
Like
so Feldera.
sawtooth window? No.
Well, no, it's not sawtooth, but it's not tiled aggregation. There's a couple of engines like Feldera, Materialized, support this type of. We can talk about it offline. Okay.
Yeah, that would be great. Indeed, we can have a 10-minute break before the next conversation starts. I would like to have one more round of applause for Vitalii and Miguel.
Nice job.